Hello friends, welcome to this video lectures on experimental stress analysis. So today my name is Avinash Parke from Department of Mechanical Engineering, Sweris College of Engineering, Pandharpur. So today we'll discuss about the chapter number 6 of experimental stress analysis. Name of chapter strain measurement, that is the electrical resistance strain gauge. So in the part 1 of this particular chapter number 6, we are going to study the electrical resistance strain gauge, their working principle and the basic constructions we are going to study in this particular part number 1. Then we'll discuss about the types of strain gauges used for the different types of applications. Then third point, that is gauge factor. So wherever we are using the strain gauges in any type of application, so at that time we have to consider this gauge factor as a constant parameter. So that value of the gauge factor we have to consider in the strain gauge applications. And then we'll discuss about the Wheatstone bridge circuit and its output. So wherever we are using this strain gauges in any type of applications, so in that we have to use the Wheatstone bridge circuit. That means if we are using the one strain gauge, or sometimes we are using the two strain gauges, or sometimes we are using the 3 4 or number of strain gauges in a single application, so at that time we have to use this particular Wheatstone bridge circuit to calculate the output of all those strain gauges. So in this last point we are going to derive even small derivation for the output of the Wheatstone bridge circuit, and through that particular formula, whatever we are going to derive, that formula is useful to find out the output of different configurations of the strain gauges. So now we'll start one by one with this particular content. Now, so the first point is the electrical resistance strain gauge. So in that we are going to discuss the basic working principle of strain gauge and their construction. So electrical resistance strain gauge is one of the small electronic device, or it is one of the small electronics chip which is used to find out all the unknown parameters. That means sometimes we have to calculate the load value, sometimes we have to calculate the pressure value, sometimes we have to calculate the strain in rotating shaft, sometimes we have to calculate the vacuum torque. So all these values we can calculate by using the such types of the electrical resistance strain gauges. So for that purpose it works on even basic principle, that is change in resistance is directly proportional to the strain value, or the change in resistance is directly proportional to the unknown parameters, because whatever the strain gauge is there, their resistance will get changed if that strain gauge is comes in contact with any loading condition or any moving component. So what is the first requirement? If I have to use the strain gauges for any type of applications, so before that I have to paste, or I have to bond that particular strain gauge on that particular specimen. And if that specimen is comes in contact with the loading, or it is in moving condition, so due to that moving condition and due to that loading condition, their resistance will get changed. For example, if the strain gauge is pasted on the specimen, it is having the standard resistance value, that is 350 ohm. That 350 ohm is the standard resistance value before application of load. But if the load is applied, so due to that application of load, that resistance sometimes it is increases, means from 350 it becomes 450 ohm, or sometimes according to the loading the resistance is also decreases, means from 350 it becomes 250. So that increase in resistance and that decrease in resistance, that values are calibrated in terms of unknown parameters. So this is the basic working principle of electrical resistance strain gauge, where it is used in various types of applications to find out the number of parameters. So for that purpose, even one simple formula they have considered, that is in the strain gauge applications, if you go through their construction, so this is the basic construction of the strain gauge. That is this is one small electronic chip which is used to find out the number of parameters, and it works on one principle, that is change in resistance is calibrated in terms of unknown parameter. So whatever the resistance is going to change, that resistance value will get changed for this particular element, which is called as a sensitive element. So this particular portion, so this portion indicates the sensitive element, which is also called as a grid element. So here it is available in the form form of wire, which is a one electrical conducting material, and whatever the resistance will get changed, that resistance will get changed for this particular sensitive element. So this is the basic construction of the strain gauge in assembled position as well as in disassembled position. So if you go through the figure number A, that is the central portion is called as a grid element, and this is called as a thin paper 1, and this is called as a thin paper 2. So the thin paper 1 is provided at the top of the grid, this thin paper 2 is provided at the bottom side of the grid, means your grid element is sandwiched in between these two thin papers, because there are three important reasons that is these thin papers are provided. That is, first reason is due to that particular thin papers, your this grid element is protected from the environmental conditions. So whatever the environmental particles are there, dust particles are there, water particles are there, if that water particles or environmental contaminants, if they are comes in contact with this grid element, so it will affects on their resistance value and it creates the error during the measurement. So to protect this particular grid element from the environmental condition, this two thin papers are plays very important role. Then second advantage, that is it will be acts as a one insulation in between specimen and the grid element. So while pasting the strain gauge on any test specimen, it is not possible to paste this grid element directly on the test specimen. If this grid element is comes in contact with the if this grid element is comes in contact with the specimen directly, so again their resistance will get changed immediately and it creates the error during the measurement. So while using the strain gauges in any type of application, there should not be direct contact in between this grid element and the test specimen, and to avoid this particular condition, so these thin papers are acts as a insulation in between the grid element and the specimen. So this is the second advantage of this particular thin paper. And third important advantage is that due to these thin papers, I can handle this particular strain gauge very easily. So the whatever this grid element or the sensitive element is there, it is very small in construction, or it is very small structure which is prepared by using very small thin wires, and whatever the diameter of wire is there, it is approximately 0.025 mm. So whatever these small dimensions are there, it is very difficult to handle. So to avoid that particular situation, these grid elements are provided in between thin paper 1 and thin paper 2, and then after at the end you will get the strain gauge in like this condition, which is indicated by the figure B, and due to this particular thin papers, I can handle this particular strain gauge very easily. So these are the three basic advantages of the thin papers. That is, first one, to protect the strain gauge or to protect the grid element from the environmental condition. Second, these thin papers are acts as a insulation in between grid element and the test specimen. And third advantage is that these thin papers are due to that particular thin papers, I can handle this particular strain gauge very easily. Therefore these thin papers are plays very important role. So this is the basic construction of the strain gauges, and whatever the this sensitive element and the grid element is there, so for that particular sensitive element and the grid element, we have considered some of the factors. That is whatever the metallic wire we have considered, that is the resistance of that particular wire is the R, L is considered as a length, A is considered as a cross-sectional area of this particular grid element wire before application of load. So whatever this R is there, its original resistance before application of load. L represents length of wire before application of load. A represents cross-sectional area of wire before application of load, means this R is directly proportional to length, but it is inversely proportional to A. That means if the strain gauge is comes in contact with any loading, and in that loading if resistance increases means what happen, the extension of this particular grid element is taking place. Extension is taking place means the length of this particular grid element is increases, but at the same time, as the extension of this grid element is taking place, at the same time the cross sectional area of this particular grid element at this particular point is decreases. Therefore, when the resistance of the grid element or the resistance of wire is increases, at the same time the length of wire is also increases, but cross sectional area is decreases. And exactly opposite, if the resistance of that particular wire is decreases, at the same time, the length parameter is also decreases, but the cross sectional area is increases. Means from this particular equation, I can say that R is directly proportional to length, and this R is inversely proportional to the cross sectional area. And by avoiding this particular directly proportional sign, I have written that particular equation in the form of one constant parameter, that is R is equal to rho into L divided by A, and that rho is called as a this rho is called as a resistivity factor. So this rho is called as a resistivity factor, which is a constant parameter. What are the constant parameter we are considering in the Hooke's law? That is, stress is directly proportional to strain, and after that stress is equal to Young's modulus into strain. So that E is also represent the constant factor in the Hooke's law application. But here R is directly proportional to length and inversely proportional to A, and after that the final equation will be written in this form, that is R is equal to rho into L divided by A, and this rho is called as a resistivity factor, which will be acts as a one constant parameter. And as we know that the strain gauge works on one principle, if that strain gauge is comes in contact with the tension, the resistance is increases, but if the same strain gauge is comes in contact with the compression, the resistance is decreases, and hence this is the basic working principle on which electrical resistance strain gauge works. So this is about the basic working principle and the construction of the strain gauges, and in that construction I have explained the importance of this particular thin papers, how the resistance of the grid element will get changed. So like that, this is the basic working principle and the construction of the strain gauge. And one of the thing is very important, so whatever the strain is transferred, for example, if the strain gauge is pasted on any component and whatever the strain is induced in that particular component, that induced strain in the test specimen or the component, it is directly or it is directly passes through this particular grid element through the layer of adhesive and the this particular thin papers, because there is no direct contact between the grid element and the test specimen, but the strain is transferred from specimen to the layer of adhesive, then from layer of adhesive to the thin papers, and from this thin paper to this grid element, and according to the loading the extension or the compression of grid element is taking place, and according to that this grid element is connected to the display, and in that display we can observe that whether resistance of this grid element is increases or decreases, and according to that we can find out the unknown parameter. So this is the basic working principle and the construction of the strain gauges. So, and we can use this particular strain gauge for measuring the different parameters, like we can use for the measurement of stress, then strain, then force, then torque, pressure, bending moment, etc. indirectly. So by using the strain gauge, it is not possible to measure all these parameters directly. So first of all we have to measure their change in resistance, and then that change in resistance are calibrated in terms of unknown parameters. Therefore this word they have mentioned, that is indirectly. So this is the basic working principle and the construction of the strain gauges. So in the construction, they have represented the strain gauge in disassembled position, and here the figure B represents the strain gauge in the assembled position. Now the next point is the types of strain gauges. So the types of strain gauges, basically the strain gauges are divided into the two types, that is metallic and the non-metallic strain gauges. Why the strain gauges are called as a metallic? Because whatever the sensitive element or whatever this particular grid element is used in any type of strain gauges, if this particular grid element is made by any metal, So this particular strain gauge is called as a metallic type of strain gauges. And the non-metallic strain gauges means semiconductor type of strain gauges. But there is a basic difference in applications in the metallic and non-metallic strain gauges. If we have to use the strain gauges in the water applications, at that time it is not possible to use the metallic type of strain gauges. In that case, we have to use this non-metallic or the semiconductor type of strain gauges, because in metallic type of strain gauges, as we have prepared this particular grid element by using a one metal. So if this particular grid element or if this particular metal is comes in contact with water, so immediately the corrosion resistance of this grid element is taking place, and due to that corrosion resistance, it affects on the reading. That means it creates the error during the measurement. Therefore, this metallic type of strain gauges are used in such applications where there is no any temperature contact as well as there is no any water contact. And if we have to use the strain gauges in the water applications or in temperature applications, at that time we have to use this particular non-metallic or the semiconductor type of strain gauges. But in this chapter, mostly we are going to focus on the metallic type of strain gauges. So according to the construction of grid, again this metallic strain gauges are divided into the two types, that is wire type and the foil type. And whatever the wire type of strain gauges are there, again this wire type of strain gauges are divided into the two types according to the formation of grid. That means whatever this grid element or the sensitive element is formed based on this particular construction, again this wire type of strain gauge is divided into the further two types, that is flat grid and the bobbin type of grid. So one by one we'll discuss all the types of metallic type of strain gauges. So first one is a wire type of strain gauges. So what is meant by the wire type of strain gauges? So whatever the strain gauges are manufactured, in that particular strain gauges, whatever the grid element is prepared, for example, whatever this grid element is prepared, if this grid element is prepared by using a wire, and that wire is having very small diameter and diameter of that wire is approximately 0.025 mm. If such types of the grid elements or the sensitivity elements are formed by using the wire, so this particular strain gauges are called as a wire type of strain gauges. So this is the basic definition of the wire type of strain gauges, that is the sensitive element or the grid element of strain gauge, if it is prepared by using a one wire, so that particular strain gauge is called as a wire type of strain gauges. And again this wire type of strain gauges are further divided into the two types, that is flat grid and the bobbin grid. So this flat grid and bobbin type of grid, again they are further divided because according to the application. So if you go through the basic construction of the flat grid, so this is called as a flat grid. Why it is called as a flat grid? Because whatever this particular sensitive element or the grid element is there, that grid element is formed in only one plane. So suppose this rectangle represents a plane of this particular strain gauge, that means only single horizontal plane is there, and whatever this grid element is prepared like this construction, so that grid element is prepared in only one plane in back and forth type. So whatever this grid element is prepared, so this particular motion is called as a back and forth motion. Therefore, if the strain gauge is prepared in only one plane by taking the wire in back and forth type, so this is called as a flat grid, or this is called as a flat grid type of strain gauges. And this particular strain gauges are manufactured when gauge length is 12 mm. Gauge length is 12 mm means whatever the length of the strain gauge is there, this horizontal length. So if this gauge length is 12 mm, or if we have to manufacture the strain gauge having the gauge length is 12 mm, at that time in such types of the strain gauges we have to prepare the flat grading. And exactly opposite, that is what is meant by the bobbin type of strain gauges. So in this bobbin type of strain gauges, if you go through its construction, so in this particular bobbin type, so whatever the wire is there, that wire is wound on a one paper tube in the form of helix. So this is a one wire. This particular vertical column is called as a paper tube which is also in circular in cross section, and whatever the wire is there, that wire is wound around this particular tube in the form of simple harmonic motion. And after that again this particular wire is again sandwiched between the two thin papers to protect that particular grid element from the environmental conditions. So this is the basic construction of the bobbin type of grid, and this particular grid is manufactured when gauge length is 9 mm and less than it. If we have to manufacture even strain gauge during manufacturing, if we have to manufacture that particular strain gauge having length 9 mm or less than 9 mm, at that time we have to prepare the grid in the form of bobbin type. And if we have to manufacture the strain gauge having length is 12 mm, at that time we have to prepare the grid in the form of flat grid. So this is the basic difference between the flat grid and the bobbin type of grid. Why this bobbin type of grids are manufactured? Because there are so many applications are there in which in such applications very less space is available to paste the strain gauge on that particular component. As there is no space, or there is very less space is available to paste the strain gauge on that particular component, so we have to use the strain gauges which are having very small size. And to prepare that particular strain gauges in small size, whatever the grids are formed in that particular small strain gauges, that grids are formed in the form of bobbin type of strain gauges. Therefore, based on the applications, if the large space is available to paste the strain gauge, so we can prefer the flat type of grading. If less space is available to paste the strain gauge on the specimen, at that time we can use the bobbin type of grid. So these are the two types of the wire type of strain gauges, in which whatever the two grids are formed, both grids are formed with the help of wire. That means in the flat grading also wire is used, in bobbin type of grading also wire is used. Therefore these are the two types of the wire type of strain gauges, that is flat grid and the bobbin type of grid. And the second type is the foil type of strain gauges. So there is a basic difference between the wire type and the foil type, otherwise the construction is same. So if you go through this particular foil type of strain gauges, so in the foil type of strain gauges, whatever the grid is formed, this grid is formed by using the foils which is having the large area as compared to the wire type of strain gauges. So if that wire is spread on any horizontal surface, there is only line contact. That means very less contact is there in between the specimen and the wire. But if this foil is spread on any horizontal surface, so as it is having some amount of thickness, as it is having some amount of width, due to which there is a large area contact in between specimen and the foil. So whatever these particular foils are there, these foils are prepared by using the photo etching process. And in this particular foil type of strain gauges, the large area is available to paste the strain gauge on the specimen. If I have to paste this particular wire on the specimen, very less space is available because there is only line contact in between wire and the specimen. But if I have to paste this particular foil on the specimen, so for the pasting purpose, the large area is available to paste this particular foil on the test specimen. And as the large area is available to paste the foil on the specimen, due to that large area, the maximum area is in contact with the specimen, due to which this foil type of strain gauges are becomes more sensitive as compared to the wire type of strain gauges. So if you go through the construction of this wire type and the construction of the foil type are same, but here the grid is manufactured by using the wire. Here the grid or this particular sensitive element is manufactured with the help of foil, and due to that foil, the maximum area is comes in contact with the specimen, due to which this foil type of strain gauges are becomes more sensitive, and it gives the better results as compared to the wire type of strain gauges. Therefore nowadays in many of applications, if we have to consider the sensitivity factor, so in such types of application, instead of using the flat grid type of strain gauges, this foil type of strain gauges are used in the such types of applications where the sensitivity factor factor we have to consider. So this is the basic classification or the types of strain gauges, that is we have discussed about the metallic and the non-metallic strain gauges, their applications. Then in metallic we have discussed about the what is meant by the wire type, what is meant by the foil type of strain gauges, and again in the wire type we have discussed about how the flat grading is formed and how the bobbin type of grading is formed, and where this flat grading and bobbin type of gradings are used in the various types of applications. So this is about the types of strain gauges. Now, now we'll discuss about the next point, that is gauge factor. So what is meant by the gauge factor? So the simple, this is the one constant parameter which is very simple, and this factor we have to consider in the strain gauge applications. So just for your example, we have solved the so many theoretical numericals in the strength of material, and in that particular strength of material we are considering so many constant parameters. For example, Young's modulus is there, modulus of elasticity is there, then bulk modulus is there, then modulus of rigidity is there. In addition to that, we are considering one constant parameter, that is mu, which is called as a Poisson's ratio. In so many numericals, in so many problems, that mu will be given as a one constant parameter, and that constant parameter we have to consider while obtaining the solution of that particular statement or solution of that particular numerical. Similarly, wherever we have to use the strain gauges in any type of application, so at that time we have to consider this constant factor, which is called as a gauge factors, and this gauge factors is one of the constant values. Sometimes it depends upon the resistance, and that gauge factor will be is available in the form of gauge factor is equal to 2, gauge factor is equal to 2.5, gauge factor is equal to 3. So like that constant values we have to set in the strain gauge applications. So whatever the strain gauges are connected to the display unit, so on that particular display unit, initially by putting the strain gauge in the application, we have to set that particular gauge factor, and then only we have to take that particular strain gauge under the application. So for that purpose, this gauge factor is introduced as a constant factor before using the strain gauges in the application. So what is the definition? So for that purpose they have considered a one condition, that is what is that condition? Consider a strain gauge having resistance R, length L of the grid element. So whatever the grid element or the sensitive element is there, so to that grid element they have considered the two factors, that is R is the resistance and L is the length. So before application of load or before the strain gauge comes in contact with the loading, R is the original resistance and L is the length of that particular grid element. If same strain gauge is subjected to the loading, that means if the same strain gauge comes in contact with the loading, its resistance will get changed and it becomes delta R, and their length is also get changed and it becomes delta L. That means after the application of load, the resistance becomes delta R from this particular R value, and the length becomes delta L from this particular length value. And by using this particular four parameters, they have defined the definition of gauge factor, that is gauge factor is defined as the ratio of change in resistance to original resistance to change in length to the original length. That means the simple definition is there for the gauge factor. It is defined as the ratio of, that is change in resistance to the original resistance divided by change in length to the original length, and the same definition is represented in the form of mathematical form, which is indicated by the capital K is equal to change in resistance upon original resistance means delta R upon R divided by change in length upon original length means change in length delta L, original length L is equal to the delta R upon R is equal to as it is, and this delta L upon L means this is the simple definition of strain. So what is the definition of strain? Strain is defined as change in dimensions upon original dimensions. So here which dimension is get changed? Length is the dimension of that particular grid element will get changed. The change in dimensions means change in length divided by original dimension means original length. So this delta L upon L is replaced in the form of strain, and by rearranging this particular term, that is by taking this particular epsilon to the left side, I have written the equation that is delta R upon R is equal to K into epsilon. So this particular value, that is delta R upon R is equal to K into epsilon, this value we have to use in next part of this particular strain gauge applications. That means wherever we are getting this particular delta R upon R, this term is directly replaced in the form of K into epsilon, and from where this particular term is defined by using this particular gauge factor. So this is the one constant factor which we have to consider in the strain gauge application. So simple definition is there for the gauge factor: change in resistance upon original resistance divided by change in length upon original length, and by replacing this particular denominator in the form of strain value and by rearranging the terms, I have written the final equation: delta R upon R is equal to K into epsilon, and I have to use this particular equation or this particular value in the further derivation part. So this is about the gauge factor, which is indicated by capital K. Now we have to discuss about the Wheatstone bridge circuit. So what is meant by that Wheatstone bridge circuit? So the basic introduction related to this Wheatstone bridge circuit and its output, that is wherever we have to use this particular strain gauges in any type of application, because sometimes the one strain gauges, sometimes two strain gauges, three strain gauges, and sometimes the four strain gauges are used in a single applications, and means if we are increasing the number of strain gauges in the application, how the output is increases. So that different derivations we are going to discuss in this particular Wheatstone bridge circuit. But before that, initially I will discuss the basic construction related to the Wheatstone bridge circuit, on which working principle it works, and also we are going to derive even small derivation for the output of the Wheatstone bridge circuit, and by using that particular output formula we are going to calculate or we are going to measure the different outputs for the different configurations. Means if the single strain gauge is there, what is the output? If the two strain gauges are used, what is the output? And if the three strain gauges are there, what is the output? So that detailed the working principle of the Wheatstone bridge circuit, its output and their different configurations we are going to study in the next lecture of this particular chapter number 6. In the part number 2 we'll discuss about the basic introduction related to the Wheatstone bridge circuit, its output and their different configurations. Thank you.